Okay, and our final speaker in this session is Caleb, who is going to talk to us about unifying static and dynamic intermediate languages for accelerator generators.
I can just like,
oh. Now it's working, yeah.
Okay, awesome. Okay, nice. Okay. Okay. So as I was saying, by accelerator generators, I'm basically just talking about a compiler for hardware accelerator design. And these compiler intermediate languages have two paradigms, static and dynamic, which I'll explain. And they have very consequential expressiveness and efficiency trade-offs. And we're going to show how you can apply the idea of semantic refinement to unify these two styles, and how that lets you build compilers that can do things that neither style alone can do. So to sort of start off with a high-level motivation is that lots of people are trying to build custom hardware accelerators for performance, energy efficiency, area, or some combination of these. And there are some examples here on the screen. And that's great, but I haven't explained yet how we're actually going to design these accelerators. So we have an idea for an accelerator, now we actually want to implement it. Because we're at a PL conference, let's just build a compiler. So I'm going to just be using a toy example, which is just simple math expressions on integers, and that's what we're going to be compiling today. So here we have a simple expression, a plus b times c divided by d. So to compile this to hardware, you just instantiate an adder, a multiplier, and a divider, and you sort of wire the inputs and outputs in correctly. And at this point, you've correctly described the structure in terms of what you're going to compute, but you haven't described when you're going to compute this, or what I'll call timing. And so that's what I'm going to focus on in this example. So the first choice is to use dynamic or latency insensitive interfaces, which I've shown in orange here. So in this paradigm, each module is going to expose a valid signal to signal when its output has been computed and the output is therefore valid. It's also going to expose a ready signal to signal when the module is ready to receive an input. And when the sender's output is valid and when the receiver's input is ready, the two modules are going to perform a ready valid handshake, and that's where the data is going to be passed. And so this is really simple. It's also very modular in the sense that if you change the timing details of the multiplier, for example, to take either fewer or more cycles, it doesn't change the interface, right? The interface is insensitive to the latency of the individual modules. But we might be able to do better. Let's say we look inside this adder, and we see that it's always going to take exactly one cycle, for instance. Then in this case, instead of using a dynamic interface, we can use a static or latency-sensitive interface. In this case, the adder is just going to accept an input, compute the output value in exactly one cycle, and then unconditionally pass the value to the multiplier. So we've eliminated the ready valid wiring, which increases the efficiency of the design. And I should point out that if you're going through all this trouble to design your own hardware, this small detail is important to you. You're going to want to, for example, be able to run your design at like a higher clock frequency, and this is going to help you do that. Let's say we look inside the multiplier, and again, we see that it always takes exactly 3 cycles. Then again, we can replace this sort of expensive ready valid wiring with a more efficient static interface. And let's say we look at the divider, but this time it's a little bit different. It has input-dependent timing, meaning it can take anywhere from 1 all the way up to 32 cycles, depending on the inputs that it's given. So if you're insistent on using static interfaces, you could just tell the divider to wait 32 cycles. This is sort of the upper bound on the number of cycles that it could take. And this is a perfectly valid way to use static interfaces in terms of correctness. But in a sense, you're being too conservative, right? Because you're wasting cycles. There's going to be times where the divider has finished before 32 cycles is up. And at this point, you're kind of just waiting around doing nothing. And so you might want to just go back to the ready valid interface from before. So to recap, that's a lot of choices, right? We have the dynamic-only interfaces. We have static-only interfaces. And then we have some sort of mix between static and dynamic interfaces, one example of which I've shown here, right? And that's our sort of first key idea here. When you're designing hardware compiler IRs, there's two choices for static or dynamic, and they have very sort of consequential trade-offs. And just as a reminder, all of these choices were just for this like really simple expression. And so that leads to the question, what about real languages, quote unquote? Languages with things like control flow that we'd actually want to sort of program in and compile that down to hardware. Specifically, for these languages where you sort of have a high-level language and then you want to generate hardware from it, how does the compiler's intermediate representation represent static and dynamic interfaces? So currently, static and dynamic compiler IRs live in separate worlds. In other words, there's going to be one IR for the static portion of the design, and then another IR for the dynamic portion of the design. And so I've sort of illustrated that here, where you have the dynamic computation using a dynamic IR in orange here, and then a static computation using the static IR in green here. But obviously, if they're part of the same design, they're probably going to need to communicate somehow. And one really way that this is done currently is by just wrapping the static computation in a ready valid interface, and that's how they sort of communicate. So like just one like pseudocodey way to illustrate this is the dynamic IR is going to be chugging along, and then it's going to sort of quote unquote call the static computation using the ready valid interface. The static computation is going to go, and then it's going to sort of quote unquote return control back to the dynamic IR, again using through a ready valid interface. But there's a few challenges with this approach. The first is that for compiler developers just have to support and maintain two IRs, which increases the work that they have to do. One example of this is like when you're performing an optimization, you first probably have to do some sort of analysis to determine if you can even perform that optimization, right? And that's going to have to analyze across two different IRs. And then also actually performing the transformation, you're going to actually have to edit the design and the intermediate representation, potentially like across IRs. And again, that just like is inconvenient and it increases work. But even worse than that, in some cases, there are certain like global optimizations that are limited by having this sort of sharp static dynamic boundary, because you're sort of separating it into two completely separate IRs with such coarse-grained communication. And I'll give a little bit more. I'll give a more concrete example of something that is limited by this later on in the talk here. So, but first I want to sort of back up and give some terminology here that I'll use for the rest of the talk. This strategy that I just described is what we call a stratified IR, where you sort of stratify the static and dynamic portions of the design into separate intermediate representations. I should also mention that there are other existing compiler IRs that sort of only just support one or the other. They just make the choice up front that we're only going to support either static or dynamic. And that's our second key idea here. Existing compilers, if they support it at all, will generally stratify their static and dynamic sections into separate either languages or separate sub-representations. And so our work is on unifying static and dynamic compiler IRs into a single IR that represents both the static and dynamic portion of the design. And we're going to use the idea of semantic refinement. So just as a reminder, semantic refinement is the following property. P refines Q if and only if P allows a subset of the behaviors that Q allows. And in the paper and in this talk, we're going to make the argument that static interfaces refine the cycle level semantics that dynamic interfaces allow for. So just to give it like a sort of illustration here, this is the same example from before, but dynamic interfaces allow a bunch of different possible cycle level schedules for the execution of each module, right? Because they're not tied down to a particular cycle level schedule. When you convert those dynamic interfaces into static interfaces, what you're basically doing is forcing the design to pick one particular schedule out of the many possible schedules that the dynamic interface is allowed for, right? So it's sort of refining the cycle level schedule of the dynamic interfaces. And it's worth sort of contrasting this with the existing approach that a lot of compiler IRs take, which is treating static and dynamic as sort of fundamentally separate behaviors, right? And this sort of manifests itself in the sort of intermediate language that these compilers use. So again, as I mentioned before, existing compiler IRs sort of stratify their representation into separate static and dynamic sublanguages, whereas we have sort of a single unified intermediate language. So I'm going to talk a little bit about our unified language now. We build on a purely dynamic language. And this is an example of it on the slide here. I don't expect you to read all the words, but the main point here is that this is the intermediate language that we build on, and it's purely dynamic. And then our contribution is that you can, on the right-hand side here, add static interfaces to this design in a very lightweight way. So you can see here, you're sort of getting rid of these done signals. You're adding a little annotation here. You're adding a keyword in the control section, but you're not fundamentally changing the IR. It's still within the same IR. And so that's the main takeaway here, just the diffs between the left-hand side and the right-hand side. And this is what we mean by unification, having a single language for both the static and dynamic portions of the design. And that's our third key idea. Our work uses the idea of semantic refinement to unify static and dynamic sublanguages. So now I want to talk a little bit about some of the concrete benefits of unification, besides just making it easier to maintain a compiler IR. But to do that, I'm first going to explain our system in a little bit more concreteness. So we build on Calyx, which is an intermediate language for high-level languages that want to generate hardware. And to give an example of how Calyx works, I'm going to use the same example as before, and here's a data flow graph from it. So the first thing to notice is that certain portions of this data flow graph perform certain computations. So this thing here performs A plus B. And in Calyx, you can encapsulate this as a group. So you first specify the computation, what's going on. In this case, just adding A and B. And then you also specify the group's done signal, when the group is done. And this is important because this means that all Calyx groups are orchestrated through a dynamic go-done interface. This is slightly different terminology than valid ready before, but it's the exact same idea. And obviously, you can sort of encapsulate the rest of the design into Calyx groups. And you can describe the scheduling of these groups using Calyx's control flow. So in this case, we're just sequentially executing one group, each of these three groups, one after the other. And again, I should note, all of these groups are control is passed from one group to another using a fully dynamic go-done interface. Another note is that Calyx also supports parallel execution, while loops, and if statements as well. So Piezo, which is our system, it's a set of lightweight extensions to Calyx, which introduces static interfaces. So on the left here, we have a group in Calyx, the same one that I was showing before. And in Piezo, if you know that a group is going to take exactly one cycle, what you can do is just basically replace the done signal, so get rid of the done signal, and replace it with this little annotation here that tells you the group takes exactly one cycle. And likewise, for all of the dynamic control flow constructs on the left here, we can introduce a static control flow construct by just sort of adding the static keyword in front of it. And again, I should point out that adding the static keyword refines the dynamic control here. So the dynamic control flow constructs in Calyx admit a bunch of different possible cycle-level schedulings of the groups. And by adding the static keyword here, you're basically restricting the compiler and forcing it to pick one particular schedule out of the many possible schedules that exist. Another thing to note is that there's no little latency annotation here, which means that the latency has to be inferred by the compiler. One thing that becomes immediately clear from this is that all child control is static. So if you have a static parallel block, all of the threads in that block have to be static as well. And because of this restriction, you can think of Piezo control as a dynamic ocean with interspersed static islands. So on the left-hand side here, you have control flow on the left, and this is like this sort of dynamic ocean. And then we have this sort of interspersed static island as one example here. And I've went ahead and I've made up a data flow graph here. I've made up the group assignments, and I've also made up these register names Y and Z. And that's because I want to talk a little bit about an optimization that we can do in Piezo. So if you notice on the left-hand side here, the control flow looks pretty similar to something we would do in like a software compiler. And because of that, we can perform a liveness analysis, the same as very similar to what you would see in like a software compiler, to determine Y and Z's live ranges. And because they don't overlap, we can share these registers. And obviously, one good thing about this is we've reduced resource usage. So instead of using 2 registers, we're only using 1. Another interesting thing is that the analysis sort of trivially spans the static and dynamic code. So in this case, Wise live range spans both the static parallel block and the dynamic part of the dynamic sequential execution. And another thing is that the register itself is shared between the static and dynamic code regions here. And it's worth sort of going back to the stratified IR to think about how you would actually implement this in a stratified IR. So you would first have to sort of perform some sort of interprocedural analysis across these 2 IRs to determine liveness. And that's obviously more difficult, but it seems definitely doable. But the part that it's not clear to me how you would do is how to actually share the same physical register across these 2 IRs. Because sort of the existing IRs, the instantiation of the physical hardware resources are sort of localized to the individual IRs, so it's not clear how you would share it across the 2 IRs. And that's a sort of 4th key idea here. Unification lets you write compiler optimizations that were either difficult or impossible before. I think I'm running low on time here, so I'm going to talk about an evaluation we used for a front end that compiles to Calyx. And I didn't talk about this in the talk, but the way Calyx works, there's an automatic pass to promote from Calyx to Piezo, and the compiler can sort of detect that. Given how sort of syntactically and semantically similar they are, it's not a super difficult pass, and it's sort of predictable. And I also didn't mention this in the talk, but you can read the paper if you want details. But Piezo is eventually compiled back down purely into Calyx. And so this gives our evaluation sort of two points of comparison, right? There's the normal Dahlia to Calyx compiler, and then there's the Dahlia to Calyx, and then promoted to Piezo, and then going back down to Calyx. So these are the sort of 2 things we're comparing in our evaluation for this example. And for performance, so like how long the designs take, we measure cycle counts normalized to Calyx, and we take fewer cycles, so like higher is better here. And then for area, we're going to use LUTs, which are lookup tables. These are the primary logical resources used on the FPGA, which is what we're measuring here. And Piezo uses fewer LUTs than Calyx. Yeah, and these are just a recap of the key ideas, and thank you for listening.
Thank you. Questions for Caleb? Will.
Hi, Will Creighton from Brown. So I'm curious just to understand better how this deals with space, in the sense that, like, if I have an adder that takes 1 cycle and a multiplier that takes 3 cycles, I might want to instance 3 multipliers. That way I can you maximize the throughput of the whole system and use the adder effectively. Would that concept, where in the system is that concept expressed? Is that supposed to be handled by the things that compile into the IR, or is that something that would be determined by at your system level?
So like if you want to instantiate like more resources to increase like parallelism, that would be like in the front end targeting Piezo. Yeah, so you would just like do that in the front end targeting. We don't like instantiate more resources to increase parallelism.
But if doing that kind of reasoning requires understanding like the number of cycles that something takes, sort of how does that interplay with the use of latency inference that your system does? Like because it seems like, for instance, if the higher level thing needs to reason about the number of cycles that something takes, but then your system is also in charge of determining that, how would you like go back and forth? Or is that just like 2 different use cases?
When I say like, oh, we know this adder is going to take 1 cycle, that's going to be provided to us. We're not going to like that's like a little annotation that you give us. Mm-hmm. Does that not answer your question?
Sorry, maybe I misunderstood. I thought there was a bit where you didn't have to specify the number, and you could let your system infer the latency.
Like this thing here.
Yeah.
Okay, so this is like really basic. All you're doing is, because it's like if you think about a tree, if all of the leaves have a known latency, and you're like composing it in this like very strict, like this very organized way, it's very easy to just propagate that information upwards. Does that make sense?
Yeah, it does.
Okay.
Thanks.
Yeah.
Any other questions? No? All right. We are 1 minute past time, so sorry for that. Sorry for the messed up mics in this session, but I think we survived anyway. So let's thank